Is it visible?
Yes, visible. Yes, it's visible. So the next speaker is Parthiv Haldar. He's going to talk about lessons from quantum information to S matrix theory. Parthiv, please go ahead.
Okay. Thank you very much first to the organizers for giving this opportunity to present the work. So my talk is named Lessons from Quantum Information Theory to S matrix theory, to quantum information to S matrix theory. So before I start, let me give a brief review of the playground on which we are going to play. So S-matrix bootstrap is a very old idea. It was first conceived by Werner Heisenberg, who wanted to develop a theory manifestly without the infinities of the quantum field theory, which today are handled by renormalization theory. Building upon his philosophy in 1960s, Geoffrey Chew championed the S-matrix bootstrap in order to construct a theory of strong interaction. That time QCD was not developed yet. Using the basic requirements of unitarity and analyticity for S-matrix, because from an experimental's point of view, S-matrix is the observable, field is not the observable. While Chew's original goal of QCD did not take off, the old S-matrix bootstrap actually paved way for the birth of string theory. The program got a modern revival in the computer-friendly 21st century, following an impressive success of the conformal bootstrap program, which is similar program, but in a sense a younger, aided by modern numerical tools of semi-definite programming. You can see all these works. It's been going on for some time now. Now, apart from the numerics-assisted revival, attempts have been made to revive the analytics as well in the modern settings. The main objective of the current state-of-art S-matrix bootstrap program is this. It's to constrain the space of physical theories in a self-consistent manner. In the sense that you start with some basic physical principles like unitarity, analytic structure, which is essentially a manifestation of causality, possibly other principles to kind of see where do the physically consistent S matrices lie, and possibly to explain why standard model is so special. Now, where does quantum information fit in the S matrix theory? In recent times, we have seen that insights from quantum information theory have been extremely successful in the realm of high energy physics. S matrix theory seems a very natural playground for theoretic analysis because scattering invariably changes entanglement structure of the scattered particles. The question is whether QI theoretic investigations lead us to new constraint on the space of S matrices, and thereby possibly lead to some kind of selection principle, which will lead us to, to select one S matrix over the other. So this talk is roughly based on this work from the past year and some work that's going on with Anindya Sinha. So what we hope to gain. So this is a picture of a result of S-matrix numerics that we did in this paper. This picture actually follows from some basic unitarity analysis, some analyticity requirements. And this blue shaded region, this river-like region, is the whole it's the whole allowed space from those constraints. Of course, you can add more constraint, you will be possible constraining. But quite interestingly, standard model seems to be living on this cross, which is like a kink-like position. So the question that you can ask is that can we constrain the allowed region in a non-trivial way using quantum information theory and possibly close on to this cross or standard model, in a rather non-trivial way. But how can we probe entanglement that is produced by scattering in a way which manifests the entangling properties of the S matrix? I mean, what kind of measure we are going to chase after, which will bring out the entangling structure of the S matrix itself? One quantity of interest, it's called entangling power, which was introduced by these people in the context of quantum information theory. So for a bipartite system, which with a state space, which you can factorize, where each of the Hilbert spaces are finite dimensional, if E is some entanglement measure over the same, I mean, it can be any entanglement measure which satisfies the basic axioms of the entanglement measure, then the entanglement power with respect to E is defined by this averaging, which essentially is that you take the entanglement measure and average over all possible states with respect to some probability distribution P. Now, as an entanglement measure, these gentlemen, they took the linear entropy, which is like a simplified version of the usual von Neumann entropy. I mean, you can obtain this from the von Neumann entropy anyway. Why? Because it was actually calculationally easy, it was easier to calculation than a full-fledged von Neumann entropy. Actually. Physically, entanglement power really measures that how much entanglement you can import upon an otherwise entangled state. The important point is that for a given probability distribution, the entanglement power is essentially a property of U, because you essentially have averaged over all possible states. Thus, one can try to make an entanglement assisted comparison between different unitary evolutions in terms of this entanglement power. Now, for our analysis, we will be mostly concerned with uniform distribution. For uniform distribution, the entangling power actually satisfies a kind of bound, which looks like this. The interesting thing is this upper bound, which is entirely in terms of the dimensions of the each subsystems, assuming one dimension is less than the other. Now, the idea of exploring entanglement power of S matrix is not new. It's been already considered in the context of low energy QCD scattering, which is by these gentlemen in 2018. And recently, it was also studied in the context of the S matrix approach of the classical gravitational scattering, which has been quite some time, by Yutin Huang and collaborators in this work. And they found quite an impressive understanding where they showed that essentially a minimization of entanglement power leads to a very specific kind of black holes, black hole scattering. Now we consider for our case entangling power of S matrix for entanglement in the isospin case in the context of 2-2 pion scattering. Why? I mean, for scattering, of course, you have various degrees of freedom. The most primitive degrees of freedom is momentum, but momentum is infinite dimensional, which is problematic. Then you can go for some finite dimensional degrees of freedom, like isospin, possibly spin. We took isospin because spin is a little bit problematic for relativistic particles. Now, in this case, each subsystem is 3-dimensional, which is finite dimension. So, we hope to then therefore exploit the bound that I quoted before to constrain properties on this matrix. So, a generic isospin particle state, we can see it as a Q-trit state. I mean, Q-trit is a 3-dimensional analog of a Q-bit. Now, the most general state, I mean, of a Q-trit, you can be represented by a point on complex projective CP2. So a single particle isospin state can thus be parameterized by this in terms of the CP2 angle, CP2 parameterization, alpha, beta, mu, and mu, where momentum P is now a very important label because momentum is always there. And this P-1, P0, P1, these are the base Q-trit. That means these are the, you can think of, essentially these are the eigenstates of the I3, the zth component of the isospin. So mu, nu, and alpha, beta, these angles satisfy these in range. Now, for the geometry, the CP2 in this, it's given a metric geometry with the usual Fubini study matrix, which has the differential volume element, which is given by this, and with a total volume equal to pi²/2. Now one can consider an initial state. So by construction, we have taken the state in such a manner that we are considering in the center of mass frame, so that the two momenta are in opposite direction. You can choose it to be in z direction or whatever, but with each of their alpha, beta, mu, nu parameters with them. Now, as a final target state, we will consider this state phi, which is obtained by first you act S on psi, but then you take a projection on the two particle state, because psi S acting on psi will produce a whole plethora of states, because you have essentially all kind of it can go to all kind of states, but you take a projection in two particle states, so that your final state is essentially a two particle state, rather a superposition of the two particle states. Here, A, B actually corresponds to basic utilities. Note that here, the important point to note here is that I have taken a particular momentum. So this Q is not equal to P, it's some other Q, but it's a particular momentum configuration. So it's not exactly a projection onto the total two particle state, rather it's a projection on the isospin sector of a two particle state for a particular momentum configuration. So that's an important point to notice.
Parthiv, you have got 5 minutes.
Yeah, okay, thanks. Now one can consider the density matrix starting from phi, the usual way construct, and obtain the subsequent reduced density matrix. And then one will have the entangling power with a uniform distribution over CP2, because actually two copies of CP2. It's not just CP2, it's CP2 cross CP2. So that you have this, division by two factors of CP2 volume, and an integration over the CP2, the entire CP2, each copies of the CP2 pi. Now on this EP0, this is essentially a function of MST, which is the scattering amplitude. I mean, it's a complicated expression, but it's essentially a function of MST. But on this quantity, since it's a finite dimensional Hilbert space to start with, because it's isospin space, you can actually put the bound, put the bound that we quoted, because EP0 is supposed to satisfy that bound. But now that will transpire in terms of a bound on this MST. Now, how to analyze these bounds, because these are nonlinear bounds, this is actually the numerics is work in progress. Finally, I would like to tell a little bit of what future directions one can take. One can consider what about the spinning particle, in general spinning particle, perhaps entanglement in helicity. For massless particles, perhaps one can consider entanglement in helicity. But for spinning particle, there is an issue of defining a Lorentz invariant, obtaining a Lorentz invariant entanglement measure, because it turns out that for spinning particle, you cannot really separate out spin and momentum. So in a sense, you have to consider the entanglement collectively in spin and momentum. So that's a challenging aspect of that. Secondly, perhaps, I mean, it's more natural, whether we can consider the entanglement power for the momentum entanglement case. But there is a problem that the momentum state is not only infinite dimensional state, but it's a different kind of infinite dimensional space, because it's already a very badly behaved space. So, you have to actually develop a quantum information theory in an infinite dimensional Fock space altogether. And finally, quantum information theoretic measures, they satisfy different kind of inequalities, like strong subadditivity or monogamy. The question is, which is worth interesting, is that whether these inequalities give the new insights to the recent programs of the positivity, because positivity constrain the space of ace matrices quite non-trivially, and whether we can obtain new insights into this positivity stuff from the Q information theoretic properties. The game is on. Thank you.
Thanks, Parthiv, for finishing in time. Questions? Sachin.
Hi, Parthiv. So, is there an example of let's say, S matrix which satisfies, say, unitarity and all the other constant, but fails to satisfy, your constraint, or vice versa?
No. We have okay. So not explicit ace matrix, because anyway, so we are testing it right now. Stuffs with the pion data that is obtainable from this ace matrix bootstrap numerics. So far that does not violate things, but we do not have any other stuff, so to speak, analytically, because we don't know how to right now. We don't know how to extract analytically anything out of it, because these are, we need to take help of the numerics anyway. We don't know. Right?
Just to make sure, your S matrices, those are unitary, etc., etc. But then on top of it, you put in this constant and you get something.
Yeah. Yes. Right.
Okay, so.
Yeah, so I was just wondering, why don't people consider constraining or bootstrapping the S matrix using the BMS symmetries, apart from the other Lorentz and translation symmetries? That would give far more constraints and kind of pin down the S matrix completely, right?
Okay, I don't know much about BMS symmetries, but I'm not sure whether a general S matrix is supposed to satisfy BMS symmetry or not. That I'm not sure. Because axiomatically, when you are looking from the axiomatic, because all this bootstrap, the entire S matrix bootstrap program was it's based on the axiomatic S matrix treatment. There, originally, you have unitarity and causality, so to speak. And causality manifests itself in terms of various analytic properties. Mostly, most precisely, it's a certain fall off in the infinity, the Regge fall off in the infinity. And people try to constrain that. Unitarity manifests in terms of positivity, but I don't know. I've never seen in the most general case, how does this BMS symmetry? Okay, first of all, I do not know about BMS symmetry much, so yeah, I can't comment on that.
Okay, Alok.
Hi, Parthiv. So my question is related to maybe Sachin's question. So the usual bounds we derive, for example, in the like angular momentum basis, the positivity constraints, they come from the usual postulates, right? So these are extra sorry, I misunderstood. So these bounds are, they are like reformulation of the usual constraints we will get from the postulates of S matrix, or they are like
So this is an interesting question, actually. So superficially, right now, with the stage at which we are, it seems like we are getting this is some extra constraint we are putting. But this is an interesting question altogether, that whether these constraints are already inbuilt inside the S matrix theory. Whether this can be. Right. This can be proved. Whether this is, maybe this is nothing new. This is already there. Whether we will be able to prove it. That will be. So I think a rather interesting take can be that whether we can go in the. So one natural thing is, obviously, you start with the S matrix inequalities or S matrix properties, and you get this quantum information theoretic stuff, and it's good. But I think a little bit more interesting would be that if you can go in the reverse direction.
Yeah, that was my next question. Because here it looks like you're only using unitarity, but if you go away, you can use analyticity and crossing.
Yes. Yeah, right.
Also, just one small question, that you varied the your state in the isospin space, but I didn't. Can you have unequal masses? Keep the momentum, but the masses are unequal, and then is it possible to generalize?
Okay. So you want to say that? Okay. Yeah, I think masses here is not really. Because we could. I think the masses, we can keep it like free. That's not a problem.
I see. That can be done.
Yeah. That's not a problem. Yeah.
Okay, Arnab.
Hi, Parthiv. Just very quick question. So I'm curious about your comment that you made in the last slide about momentum space.
Yeah.
So is there anything specific that you have in mind? In particular, for example, do you want to consider, let's say, shells of momenta, and you want to say that the Hilbert space has a factorization across those shells? And you want
so for example, this considering considering this entanglement in momentum, it's it's not new. People have done before us, obviously. But usually we consider this like this Fock space states, like this this P states, this asymptotically free states. Now that is essentially, and you vary over the entire momentum space, and you get obvious infinities because your Hilbert space is infinite dimensional. but this is not. I mean, the way we work with the way all those Fox space states are, they are not even a Hilbert space. They are technically they are like the single particle state are. There's not even Hilbert space. It's a rigged Hilbert space.
Right.
So I mean, so how do you? So for example, will there be a bound like that we obtained before? And after taking care of infinities, I mean, nobody have studied it. So I think you have to just work on.
I was actually curious about whether you can, I mean, or how you define even operationally the density matrix and the reduced density matrix, for example.
Operationally we define in the usual manner. So suppose you have, so let's say you have a two particle state. So suppose you have two momentum, like, so just forget about the isospin and all that. You have just momentum. So it's like PQ. And then you have S acting on the PQ, but then as usual, you take a projection on the two particle states. Let's say KL, but then you integrate. So now when you're taking a projection, you have actually basically integrated over these KL states. Now from that phi state, you actually construct your density matrix, but now it will consider a bunch of momentum integrals. Then when you do the reducement, I mean, this you can do formally, of course. We do it formally. Now, obviously, you can ask more mathematical questions that we have not checked, but that's how people do it formally.
Okay. So I mean, I was just trying to understand whether you need a Hilbert space for this or just a Fox space is enough. Yeah,
I think Fox space. So we have worked so far in Fox space, but obviously, yeah, you can ask this question and how much mathematically they're correct. Mathematical rigor question, that's a different thing.
Okay. Thank you.
Yeah.
Okay, Parthiv. Let's thank all the speakers for this session. Partha, Pranjal, Gourav, Aranya, and Parthiv for keeping in time. Let's thank them all. Hello.
Thank you so much, Sheshansu, and indeed all the speakers. So let's reconvene at 2:15 again, 2:15, please. See you then. It'll be a post-lunch link. Remember that. Thank you.